Okay, so I can go ahead and replace my nonlinear device with a resistor in order to find out the small signal behavior, and I can really create a circuit in order to do this. So what I'll do is, if this equation is captured by the large signal circuit, then the small signal expression can be derived from the small signal circuit, and it is really simple. All I have to do is the following. Okay, I take the same circuit, okay, and I replace the device, the nonlinear LED, with its small signal behavior. Okay, so here I get a resistor behavior ID, where the resistance R is equal to 1 divided by ID times B. Okay, so for the purposes of computing the small signal behavior of the circuit, I replace the device, the LED, with a resistor, as shown here. And then I'm going to construct the exact same circuit, the same topology. Okay, then I'm going to replace the input source here with the small signal component of the input. Okay, so here I replace the input with the small signal component, and I replace the LED with its small signal equivalent, which is simply a resistor. Notice the device behaves like a resistor for small signal values. What is absolutely amazing is that if you look at the small signal circuit, it is a linear circuit. Okay, my small signal circuit is linear. Okay, I've replaced the LED with the resistor because the LED behaves like a resistor for small signals. And then I've taken my source and replaced that with the small signal part of the source. So this is my circuit construction. I can take the normal circuit and simply replace each of the components with their small signal equivalents, and I can directly go ahead and analyze the circuit in order to get the output. And in this case, notice that I can go ahead and analyze this circuit very trivially. So notice that in this case, ID, or ID, which is the current through the device, which is the output I care about, is simply given by VI divided by the resistance R. Done. Trivial. Okay, where R is given by IDB. So this is the same as IDB. Okay, the exact same thing that I had gotten mathematically, just that here I have derived it using a circuit technique. So before I conclude this piece, I should go ahead and summarize the small signal circuit method, and we shall use that extensively in 6002X. Okay, the small signal circuit method has three steps. You start by finding the operating point using the DC bias inputs from the large signal circuit. Okay, and this typically involves a nonlinear analysis. Typically involves a nonlinear analysis. So the second step, what you do is you develop small signal models, okay, or linearized models or incremental models. They all mean the same things, okay? Small signal, linearized, or incremental models for each of the elements in the circuit around the chosen operating point. Okay, you chose the operating point in the first step, and then you go and create linearized models for each of the elements. Okay, recall for our device, the models often depends on the operating point values chosen. Remember, for our LED, R was given by 1 by IDB, and notice ID was an operating point value. So in general, the large signal model for a device might look like this. So if I have a device and I put a voltage VD across it, and I take a current ID, and let's say ID was some function of VD, and let's say this is nonlinear, then the small signal model is given by this expression. So here's my device. So it's a small VD and a small ID to reflect the small signal currents. And I get ID by linearizing the device. And the way you get that is by taking the derivative of the function f of vd. So you take derivative of the function f of vd. Oops, let me start over here. You take the derivative of the function del f of vd del vd, and you evaluate that at the point vd equals capital Vd, okay? And then you multiply that by small vd. So you replace the device by its small signal model, and the small signal model has the device giving you a small vd and a small id, where the small id relates to small vd by multiplying small vd by the slope of the function f of vd at the point vd equals capital Vd. All right, so that gives you the small signal model for each device. Okay, so as step two, you replace each of the original elements in your nonlinear circuit with small signal models. Okay, and the small signal models are characterized by small signal ID and VD, where the ID and VD are derived from the nonlinear device equation according to this formula. And then as a third step, you simply take your resulting circuit, which has all the small signal elemental models, and you go and analyze it. And the beauty is that the resulting linearized circuit is linear, and you just have to go through a linear analysis in order to get the circuit response. And the beauty of that is you can use all kinds of techniques like your linear techniques like superposition, Thevenin, etc. apply. Okay, you can use these techniques that apply for linear circuits to these resulting circuits. And part of the reason is that for most of these elements, what you end up with is these resistive elements that are linear elements. Okay, so virtually all of these the non-linear devices turn into very simple resistive elements with their linear response. Okay, your sources will turn into either open circuits or short circuits. So think of that as infinite resistors or zero resistances, and other nonlinear devices will turn into these small resistors where you get ID versus VD related as shown. All right, so the next section, what I would like to do is I would like to spend some time discussing how we go about deriving the small signal linearized models for each of several types of elements that we have. Okay, and we can derive linearized models both for linear elements like resistors. You can also derive them for all kinds of non-linear elements. Okay, and we'll go ahead and do a few examples, and then in the future you should be able to write down these non-linear models pretty much by inspection. Okay, so let's get right down to it.